Welcome to the lectures on fundamentals of MIMO wireless communications. We have seen in the previous lecture how do we get a spatial diversity. In summary, what we have seen is that by adding an extra antenna at the receiver, we can get another copy of the same signal which is transmitted, and using this particular signal we can use combining techniques by which we could at least improve the probability that the signal falls below a certain threshold. There are many techniques by which you could do it. So, we begin with one of the very simple techniques and very effective ones, which is known as selection combining. So, let us look into selection combining. So, we will start our study of selection combining. So, as the receiver suggests, as this particular name suggests, this is made of two words, selection and then combining. So, it is straightforward. In this case, we have one transmit antenna and we have more than one receive antenna. So, we will initially spend time on single input multiple output, and these different antenna branches, they send their signal to some combiner. So, the signal from the different branches are combined, and the combining technique is selection. That means, it selects the best out of it. So, there is a switch, you can imagine there is a switch which goes through all the input branches. So, it goes through all these input branches and it selects one of them, and the method is basically the one that we have discussed in the previous lecture. So, suppose with time, this is the time axis and this is the received signal strength axis. So, this is the signal strength of one of the antennas, okay, and if the strength of the other antenna is something like this, and the strength of another antenna would of course be another color, of course, it could be something like this and so on. And the selection combining is precisely what we have discussed in the motivation for this kind of work, is the one that selects the best. So, that means, here onwards at the output of the combiner, the result would be the highest signal strength. That means, we are going to select the branch which is having the highest signal strength. So, if I take black as branch 1, that means, if I take this black as branch 1 and then let us say the blue as branch 2, the blue as branch 2 and the green as branch 3, then we can say that we are basically now going to branch 2, then it is branch 3, then it is branch 1 which is the highest, then it is branch 2, then again it is branch 1, branch 3, 2 and so on. So, when we use the selection combining, it is basically what we have done before. What we are seeing is that the level crossing rate changes. We have discussed level crossing rate. So, if this is a level crossing rate, it has changed significantly in this particular diagram. The average duration of fade has changed significantly. In other words, what we can also see, as if there is a change in the average of the signal. We could also note, so there is change in LCR, level crossing rate, there is change in average duration of fade, the two very important things. What we can also see is that there is change in average received signal strength. And the next thing, which is not very straightforward appearing from this, but if one looks very carefully, one can find it out. If we follow, let us say, the blue one, let us follow the blue curve. If we look at the blue curve, the range of fluctuation is from here, sorry for this, the range of fluctuation is from this point to this point, right. So, this is the dynamic range of the blue signal. If we look at the green signal, the dynamic range is from here till here, almost similar. If we look at the black signal, it is also very similar, at least in this window, it starts from here and goes till here. So, black window is there. instead of these, if we compare the dynamic range of the red signal, what we see is the max value is somewhere here and the mean value in this particular picture is somewhere there. So, what has happened? The dynamic range of the combined signal has also reduced. Now, since the dynamic range is reduced, so what we are saying is if this axis is the mod of the received signal squared, let us say, that means for the blue one or the black one or the green one, what we have is the signal is fluctuating a lot in this range, right, whereas the red colored signal, that is after combining, what we see is that the fluctuation range is less, it's fluctuating less in this range, right. The peak is similar, but lower range has reduced. So, what we can say is the variability of the combined signal is less, okay, whereas the variability of the other signal is more. The average has shifted from the previous value. So, average was here, average has shifted, variability has also reduced, and we will study what is the impact of these changes on the performance of a typical digital communication system. So, here what we do is we will start writing our expression. So, let us say that y of I is the received signal is basically h I of h I times s plus w I. S is the transmitted signal, h is the channel coefficient, and w is white Gaussian noise, additive white Gaussian noise, y I is the received signal. So, I indicating the ith branch, and I is equal to 1 to 2 to 3 up to m r number of received branches. H is flat, it is slow, and it is basically a stationary process. We have already said we will assume Whiteson stationarity, uncorrelated scattering, and homogeneous channel for this. And when we do the selection combining, we would simply rewrite the equation as y I and put a star is equal to h I star times s plus w I star, where I star is equal to arg max of mod of h I squared over I is equal to 1 2 up to m r. What this essentially means is that this is the received signal in the ith branch. So, whether I is 1 or m r, what we see is that the same received signal is being captured, but it is weighed by a different complex coefficient, and there is something else that is added. As a result of selection combining, that means when we are doing this particular combining here, as we are doing it here, what we see is that the best of them, best in the sense the highest branch is taken during combining. So, the process of combining can be written down in this form, as we have written. Argmax means the argument which maximizes this expression, and the argument is over I. So, we will select that particular branch which has the maximum value of the channel at that instant of time. So, I star is the solution of this case. So, clearly in one case it was branch 1, branch 2 or branch 3 at each instant of time. This is what we get, and the SNR, that means each of the branch, each branch experiences an SNR represented by gamma I, which is equal to mod of h I squared times E of s squared divided by E of w I squared. E s I squared is the signal power, E w I squared is the noise power, I equals to 1 2 up to m r. E of w I squared would be equal to sigma omega squared, and E of s squared would be equal to P s. So, this is the convention that we use, and E s squared over E w I squared would be represented as gamma, which would be P s by omega squared, right. And we also have the assumption that E of h I squared is equal to 1, and E of h I is equal to 0. So, this is for Rayleigh fading, but this is always true is one of the assumptions that we make in this work. So, in case of exponential distribution, what we can write is PDF of the SNR. That means, when this is Rayleigh, this is chi-squared or exponential distribution is given by 1 by capital gamma e to the power of minus gamma I by capital gamma, where gamma I is greater than or equal to 0. We could also write it as 1 by gamma bar e to the power of minus I by gamma bar, and of course this. So, basically meaning this is the average received signal strength. Now, if you take the expectation of gamma I, which is equal to gamma bar or capital gamma, expectation of gamma I, it is expectation of this times this, that is E of Hi squared times expectation of this, which is that itself. So, basically gamma bar, E of Hi squared is 1, that is basically gamma bar. So, this is what you have. So, this is gamma bar is the notation which you could write for this case, and we could calculate the outage probability. One could calculate the outage probability, that means probability that the gamma I is less than or equal to some gamma threshold. Let us say it is gamma th or gamma 0, could also write it as gamma 0, is basically probability that gamma I is less than or equal to gamma th, which is equal to integrate from 0 to gamma threshold p of gamma I d of gamma I. So, if you continue with this, you are going to get that is equal to integrate from 0 to gamma threshold. What is p gamma I is 1 by gamma bar e to the power of minus gamma I by gamma bar d gamma I, and this if you would solve would turn out to be 1 minus gamma th by gamma bar. Okay. So, this is the probability that signal falls below the threshold. Now, when we do this particular calculation, we have done for any one of the branches. So, for any one of the branches, this is the probability signal falls below the threshold. So, if we go to this particular figure that we have drawn here, if this is my gamma th, suppose now I change this axis to SNR axis, this is the gamma threshold. So, the area under this would be, if we draw the CDF curve, if we take the average times things below this line compared to the total signal strength over the entire time, what we are going to get is this particular probability. That means, the percentage of time signal remains below the threshold. So, yes, so this is the particular probability that the signal falls below threshold for any one of the link. Okay, this is very important. So, we can write this as P out or P 0 is the probability that signal falls below the threshold, or you could also write that P 0 is equal to 1 minus e to the power of minus gamma th by gamma bar, and then you could say that gamma 0 or 1 minus P 0, if I bring 1 minus P 0 on this side, it will be equal to e to the power of minus gamma th by gamma bar, and then you could write ln 1 minus P 0 is equal to minus gamma th over gamma bar. If I move the minus side on this side, you are going to get ln 1 minus P 0, because minus is here, minus goes on top, is equal to gamma th by gamma bar. And if I would take this as the ratio and take the log base 10 on both the sides, then what we have is 10 log base 10 of gamma bar by gamma th is equal to, we could write minus log 10 of ln 1 minus P 0, right. This could be the expression. So, if you look at this, what we have over here is 10 log base 10 gamma bar, we could say it is SNR in dB, we could say it minus 10 log 10 of gamma th. So, this difference that we are seeing is basically the fade margin. It is basically the fade margin because this is the average SNR in decibels, and this is the particular threshold that we are talking about. So, if we want the signal to have a certain outage probability, then the difference between the average SNR and threshold should be given by this particular expression. So, this is with this we can find how much of fade margin that we require. So, if we go to the previous page, yes. So, here we had talked about the fade margin. Here we had talked about this margin, that means this gap. This gap is what we have talked about in this particular figure, is basically the margin. So, it is the difference between the average SNR when margin is used and this threshold. So, if I would maintain this extra amount of SNR, then I could obtain this certain particular probability of P out which I desire. So, and this is the relationship that has to be used in order to get this particular calculation. Now, as we move ahead with this selection combining, what we see is that the outage probability for selection combining, now this is different. We have outage probability for selection combining, I write in short SC, is that all M branches, here we assume independent, that means we are assuming the separation between the antenna elements is sufficient, that means it is more than the coherence distance, or it is more than lambda by 2 in case of p theta equals to 1 by 2 pi. That means they are uncorrelated. In case of Gaussian, they are independent. So, we will be assuming independent branches. For independent branches, when received signals are received simultaneously amongst all the branches. So, basically outage probability for selection combining is that all M branches combined together have SNR, that means gamma combined is less than a certain threshold. This is what we want. So, basically what we are saying is that probability that gamma 1 SNR of first branch, gamma 2 SNR of second branch, let us say gamma ith branch up to gamma MR. So, basically you have MR number of receivers are all simultaneously less than a certain gamma threshold. If they are all independent, this will be 1 minus e to the power of minus gamma threshold by gamma bar multiplied by that of the second and third and fourth, because each one is this would be raised to the power of m. So, this is the outage probability for selection combining given a certain threshold. I would put selection combining over here, and probability that this is the coverage probability that SNR, signal to noise ratio, is greater than a certain gamma, then for one or more branches is basically probability that gamma I is greater than certain SNR is 1 minus Pm of gamma, which is 1 minus e to the power of minus gamma by gamma bar raised to the power of m. And if I would if I would like to calculate the PDF of gamma, the density function of this, we take the dd gamma of the above expression, and this would lead to m 1 minus e to the power of minus gamma by gamma bar raised to the power of m times gamma by gamma bar e to the power of minus gamma by gamma bar. If you do the derivation, you are going to get this, and the mean SNR can be obtained by integrate 0 to infinity p gamma m selection combining gamma d gamma, and this would result in gamma bar sum over k equals 1 to capital MR 1 over k. So, this is the expression for gamma bar m selection combining. So, what we get to see is that there is some increase in the average SNR, and the SNR is as if added by 1 plus 1 by 2 plus 1 by 3 plus 1 by 4 and so on. The gain decreases as there is more and more number of antennas, and now this can be understood quite easily if we take a look at this, or we can draw a new figure. So suppose we have one of the branches, and let this be the signal to noise ratio of one of the branches, and the second branch would have a signal to noise ratio which is like this. The third branch may be following this particular one. The fourth branch could be this one. Fifth one, I am adding, simply trying to add more and more branches now compared to the previous pictures, and trying to ensure that their average SNR and their swing is the same, so that later we can do this combining. Okay. So after as many branches, we have 1, we have 2, we have 3, we have 4, and we have 5, we have 6. We have drawn so many different branches. So now if we try combining them, what do we see pictorially? Pictorially, I'll use a thicker color here. Yeah. So I trace the peak of it. So this is random imagination. Again, what we see is that if I take more and more number of branches, this becomes more and more stable. So if I would add another branch, let's say I would add another branch to this whole thing. If I would add another branch to this whole thing, and of course this is yellow, it's very difficult, and I add one more branch with a certain color, let's say pink. Yeah, and carry on doing it. Then what do I get? When I modify selection, my curve would now become this. Instead of dipping further, the curve would become this. Instead of dipping down, the curve goes there. Instead of dipping down, the curve goes there. So what we can clearly see, instead of dipping, it is there, it is there. The variability even decreases further. So as it increases, the average SNR increases, of course, but the gain from more number of antennas is less, and this gives you, of course, some benefit. Now if we have to calculate the probability of error for this particular case, probability of error calculation, the average probability of error. Now this is very important for wireless communications. What we are seeing is that the signal strength is fluctuating clearly because there is a channel. The signal strength is fluctuating because H is random. So if H is random, SNR is fluctuating as per this PDF, then what's going to happen? The probability of error in case of AWGN for a QPSK could be Q function of root over 2 gamma b, let's say the SNR per bit, and in that case, in our case, this SNR is not constant, because SNR we have seen per branch is equal to Hi squared times gamma bar. Previously this was constant, now it is constantly fluctuating. So we have to get the average SNR. To get the average SNR, we have to average the error probability with P of gamma t gamma. This is very important. So when you do this, the error probability that you get by using this PM is pretty complicated because the expression we have already seen before in the previous expression, and if that particular expression we have to use, if we have to use this particular expression, it's not very easy to get it through analytical techniques. So we have to use numerical techniques. Generally it is numerical techniques, and for m is greater than 8, we can remember that the average probability of error turns out to be less than that of AWGN. So this is quite interesting. We will see some of the error probability curves later on. So even with this very simple techniques, you could improve the outage probability significantly, as we have seen over here with this particular expression. So, whatever, suppose the outage probability of a single branch is, let us say 10%, 0.1, and I have 2 branches, that means I have m equals to 2, then the outage probability would become 0.1 raised to the power of 2, that means 0.01. So, just by virtue of having the second antenna, the outage probability from 10% will drop to 1%. So, if I add m is equal to 3, this would be 0.1 raised to the power of 3, and that would be a significant reduction in the outage probability. And on the other hand, we will be getting the probability of coverage from this particular expression, and that would from this particular expression, which would again be 1 minus of the probability given by this particular thing. So, this is what we have calculated from a single branch. From 0.1 it will go to 0.01 the moment it is squared, and then it can go to 0.001 the outage probability, and the coverage probability from 0.9 it will become 0.99 to 0.999. So, it is highly covered. So, if you have 3 branches, there is hardly any chance of outage when you do selection combining. So, that is a great advantage that multiple receive antennas can provide us, and that is why multiple receive antennas are highly favored. And in this selection combining, the advantage that we get is that if we try to look at the previous pages, yeah. So, there we said that cost goes up. Of course, that is true, but in case of selection combining, if we are measuring the branch and using only one of them, then we could reduce the complexity over here and could have a simpler receiver architecture, and then the cost rise may not be that high. But the problem here is that you have to constantly measure the received signal strength, that is as given in this particular expression. You have to continuously measure it. So, there is a slight variation of techniques that can be used, and that is known as switched combiner, switched beam combining. In that, what is done is if the received signal strength fluctuates, let us say like this, in one of the branches, we will take just 2 branch for simplicity. The second branch is, let us say like this. So, in that case, one would decide a particular threshold. Let us say this is one threshold, right, and they would not do unnecessary switching. The switching would happen only if only when the signal falls below threshold. So, if one is following the black, it will carry on till the point it goes below the threshold, then it jumps to the red one, follows through, and now there is no other option. So, it has to go down and then select the black one, no other option, carry on, then go to the red. Now, when it is there is no other option, you simply can't do it, but the moment I mean, you just simply don't switch, because if there are, I mean, this, if there is another, let's say we redraw this, suppose one of the branches is having this particular, this is the structure of the SNR, and the second branch is having an SNR which is like this. So, in this case, suppose we have decided a threshold which is here, yeah. In that case, the combiner would work like this. It is going to select one branch, it is going to go with that branch until the signal falls below this threshold, because the signal is pretty good. When it falls below the threshold, then it jumps to the next one and it follows through. So, here it is here, and then it switches, even though the blue one is going better, it carries on with the black till it reaches this threshold. At that point, it switches. Here you can't help it, here it crosses over and then switches. Here it would cross over, at that point it would go to the switching, it would stick with the black, then it switches, it would stick with the black, The reason, the advantage of this is unnecessary switching is reduced in this particular technique, and the complexity can be well handled. So, this is a rather more practical technique which is also used in case of selection combining. With this we complete at least one technique of receiver combining, and through which we can get special diversity gain. The BER curves are of course not very straightforward, they have to be calculated. We will see some of the BER curves, and with this we would like to move on to the next diversity gain technique, which is known as maximal ratio combining. Thank you.